Hello and welcome to episode 9 of the TechSite webinar series entitled Pioneers in Digital Diagnostics. Today our episode is titled Beyond the Lens, Advancing Digital Pathology with Advanced Imaging. We welcome you. Thank you for spending the time with us and our guest presenter, Kevin Kelly from Pramana. We invite and welcome you to make any comments or ask questions in the chat. Those will be addressed at the end of our presentation. Let me introduce Kevin, our guest presenter. So glad to have you, Kevin. Kevin is a solutions architect there at Pramana. He's got over 16 years of experience in architecting hardware and networking systems for digital pathology. He's done that with Aperio and Leica and now Pramana. In his current role as Director of Solutions Architecture for Pramana, as well as his past experience as an applications and systems engineer. Kevin has supported industry leaders to stand up really complex digital pathology workflows and infrastructure for storage, for access, and computational processing of anatomic and clinical pathology data. So, Kevin, we're delighted to have you, and I'll turn the floor to you in here just a moment. A bit about our agenda. I'll share 2 slides briefly about TechSite. For many of you, that will be a review. And then Kevin will walk us through some things around the history of digital pathology today, and how good AI really does require good data. Again, submit your comments, your questions. We really appreciate the time today. So just a bit about TechSite. We are an AI and workflow software company that has been built to enable laboratories across the human or medical, the veterinary and environmental markets to be more efficient and accurate and to positively impact the health of all of those patients throughout the world. And we have really appreciated our collaboration with Pramana and with other scanner manufacturers as well. Our AI and workflow software is compatible with scanned images from several scanners, but Pramana has been an incredible partner who has helped us to simplify many of the scanning processes in certain applications. And TechSite itself, we are more than just AI. We have built a software platform that is workflow plus the AI, and we have about 150 staff globally. And on the right-hand side, you can see our platform, the AI and workflow software platform really is, it's certainly an IMS at a minimum, where we can ingest images and let users and laboratories tag, annotate, collaborate, consult, share, all of that. But we also enable integration with the LIS and EHR. We can even enable third-party algorithms. And we are a platform that allows folks to do workflow and AI digitally across anatomic pathology and clinical pathology sample types. We are the world leader at enabling that addition across AP and CP, tissue, liquids, and cells. So again, we appreciate you giving us this time today and letting TechSite introduce you now to Director of Solutions Architecture, Kevin Kelly at Pramana, and hear Pramana's thoughts as a definite world leader in digital imaging. Kevin?
Thank you so much. And again, the invite is flattering. So today I'm going to talk about Beyond the Lens, Advancing Digital Pathology with Advanced Imaging, and what that means. First, let's go through a little bit of history. So digital pathology actually can be traced way back to the 1600s, late 1500s. The inventor of the first pseudo microscope, I call it a pseudo microscope. If you look, it's more like a telescope for tissue. But that is the first recognized microscope, believe it or not. Zacharias Janssen invented it. It laid the foundation for microscopy as we know it today. Of course, in the mid-1850s, Rudolf Virchow developed the concept of cellular pathology. So you combine this way to look at some tissues with the concept of cellular pathology, and you start moving this industry forward. The first steps towards true digital pathology, that happened in the 1968 or the mid-1960s. They started using microwave transmission, which they used already for telecommunications, to actually send images, and they send a black and white photo of a blood smear, as you see there. So that's technically the true foundation of digital pathology. Move forward, in the 1990s, you had Bacchus Labs invented the first digital pathology platform or system. It was called BLISS, for Bacchus Labs Incorporated Slide Scanner, which is a cool name. But basically, it was a microscope optimized and automated with software to put a composite image together of a tissue slide. Fast forward now to the 2000s, another decade later, and you have companies like Aperio and Hamamatsu who furthered digital pathology by going away from microscopy-based platforms and making a dedicated slide scanner. That dedicated slide scanner had advantages, and microscopes couldn't do what it needed to do. And then you get to modern digital pathology, which started around 2010. You started seeing computational pathology come about. Image analysis started making an appearance, facilitating better use of the tissue that you already captured. You also now saw sharing of large digital pathology files for consults or tumor boards, second opinions, whatever you want. You also started seeing storage start growing as the world recognized that digital storage was now going to become just as important, if not more important, than physical storage of archived slides. And then, of course, today, the digital pathology ecosystem, it includes all kinds of things: whole slide imaging, telepathology, AI algorithms and applications, integration with LIS and HIS systems, you name it, it's there. It's a giant ecosystem, and it's spreading bigger and bigger every day. But first, let's talk about the data. So in the beginning, they wanted to replace microscopy, or they wanted to use digital pathology as a substitute for traditional microscopy. In other words, they wanted to capture an image for an eyeball. Instead of looking through a microscope and then moving the slide around manually, they wanted to capture it digitally so that it could be more easily shared, more easily viewed, and faster. Imagine you could share almost immediately through email and a link, instead of having to send a flat of slides, a case work of slides, to another location via courier. And then it sits on someone's desk in another stack of different cases until they get to it. Now you could share it instantaneously and ask for an opinion instantaneously if the person had a few seconds here or there to just take a look. So it was about images for eyeballs, and that process didn't change much. And unfortunately, it actually was an ancillary process. They were still using microscopes to look at the slides. They would capture them digitally after the normal pathology process and then use that for additional steps like consults and tumor boards or research and education. But it was actually an added step. Eventually, computational pathology evolved. So now you can analyze those digital images, but again, as a post-microscopy, post-digital acquisition process. And oftentimes in the beginning, more focused on research than diagnosis. So unfortunately, in a lot of ways, it works like this today still. There are some early adopters trying to move that bar forward, but it doesn't have to be this way. It doesn't have to merely be an image for an eyeball. It just kind of is. And why? Well, because we need to evolve. If you've ever talked to a programmer, if you've done any programming in the past, you've heard the phrase GIGO. GIGO is a little catchphrase to remind programmers every day that they're writing code that if you write bad code, you will produce bad output. Garbage in, garbage out. And it holds true to a lot of different realms. I've lived with this mantra my whole life in other ways, but particularly for data, it makes sense. Tissue is not two-dimensional. It's actually three-dimensional. Even a nice, sharply sliced piece of tissue is still three-dimensional. Microscopically, that surface is never flat. It is very convoluted. And of course, it becomes more convoluted with other challenges. Dull microtome blades, challenging tissue like brain or bone, or tissues that aren't even normal FFPE sliced tissues. They could be aspirates and smears, right? Cytospins, so cytology, microbiology, hematopathology. These are all very challenging because they don't have a surface plane. So how do you use traditional monolayer scanning to capture either first a convoluted monolayer or even worse, a tissue type that doesn't have a single surface plane. So the industry targeted scan speed in the early days. They decided that as we evolve, we would start one-upping each other, and I participated in all of it, and I apologize, on scan speed. Mine is faster than theirs is. And then the next one would come out. Mine's faster than theirs is. And they just kept focusing on scan speed. And I think that was a disservice to the future of our industry. It drove the quest for speed, but it also drove an almost latching to that two-dimensional capture, that monolayer capture. Quality is always more important than speed. Sometimes it's balanced, right? You have a frozen section. You need to balance quality and speed together because you need results fast. But you can have the best quality with those speed constraints. But data enrichment is also really important. So why would we leave the data behind by focusing on speed? And when performing image analysis, more data is always better, almost. In the earlier days, a very small percentage of images, they were actually used for analysis. It was, again, a post process. You handpicked the ones you wanted to analyze, and you did it to a few, and it took a while. Now it's evolving. Now it's evolving to the point that for some workflows, every image will be analyzed. And therefore, if every image is going to be analyzed, well, then the capturing of that image has to evolve to support that process. So how do we embrace the future and empower our industry to solve health problems as efficiently and comprehensively as possible? Well, we do it with better data. It's all about the data. It starts with realizing that data is key, and the more data we have, the better the solution. Not just image data, although that is a type of data, but supporting data, stain type, tissue location, tissue age. There's even more. You can get into environmental data, hereditary data, genetic data. All kinds of data can feed into a better process. Past diagnoses, it just keeps going. Whole site imaging systems and IMS, they interface with laboratory information systems and hospital information systems all the time, but not in the way that they should. Bidirectional interfaces are commonplace, but not to put that data into the analysis. It's just to put that data into a report. How do we get that data into the process of the solution? So embracing all that different data and the sources of that data will expand our horizons. And then, of course, I did say images are data. So before I go into the slide, I want you to look at that image I have on this slide on the right side. If you think back 20 years, we started seeing navigation systems in cars, and they were all two-dimensional navigation systems. You saw an overview of a map with a guidance route, some other colored line, and when you come up to an intersection, it would give you a prompt to turn right in 0.5 miles, and it would show you where you're going to turn right. But all you saw was a line with another line showing you where you're going to turn and a rough distance estimate to when it was going to happen. You didn't see what type of interchange it was going to be. You didn't see any of those normal geographic markers that we're used to using when we drive places that we remember. And then it evolved into three-dimensional navigation, as you see on the right side. Now you know I'm going to turn right before that big, tall blue building, and it makes it a lot easier to do. There's very few missed turns anymore with 3D navigation. Well, whole site images are the same. So in a traditional tissue slide with a monolayer, anything that's out of focus cannot be effectively analyzed. It's that bad or garbage data, right? Garbage in, garbage out. That's why capturing the best focus is needed for the best output. And honestly, the industry does a pretty good job of trying to get the best focus. But if we open our minds, consider that there's always more than that single plane, then we start to consider the real possibilities. We strive for good universal focus, but remember, there's Z-range limitations on that monolayer. Most systems cannot keep going up or down as much as they want. There's some metric that limits how far they can go within that focal range. So that's always going to be a limitation to monolayer image acquisition. Many do have the ability to expand that, but you have to actually add a profile or change a setting. So it's really hard to resolve those large changes in the Z-axis, and that results in focal challenges. Z-stack scanning allows for the deepest Z range. You can add as many layers you need. You can change the offsets. You can move them up or down, whatever you want to do. but it takes longer and it creates very large file sizes. So Z-stacking is kind of hard to do on every slide. That's where volumetric scanning comes in. So volumetric scanning captures the advantages of Z-stacking. It does still use a full Z-stack, and it can be whatever you want, just like a normal Z-stack. But it eliminates the size penalty because it then interrogates all those layers, trying to find the best focus for that field of view or pixel. And then it flattens all those best pixels together to create a true universal focus. A pixel right next to another pixel. This one could have come from layer 3, and this one could have come from layer 0, and the other one could have come from layer -3. And in doing so, you get a truly universal focus. And additionally, when a scanner is designed and optimized for full-time Z-stacking, instead of as an ancillary process to be done reactively, it can be made more efficient. So it's much faster at doing the task. So if you optimize for Z-stacking, what you'll find is that if every slide gets Z-stacked, instead of it being a straight multiple, which is the traditional penalty for Z-stacking, if it's got 3 layers, it takes 3 times as long and the file size is 3 times as large. With volumetric scanning, now what you'll find out is that while the file size is not 3 times as large, it's the exact same file size if you flatten all the stacks, even the time has been minimized to 50 or even 20% of the normal Z-stack time. It is slightly longer than monolayer acquisition, but not much, and it's worth it for the quality and the data that we're going to get. And then finally, if you wanted to, all those additional layers, they can be saved. They don't have to be discarded or flattened. And in doing so, you get even more data, because while those layers might not have something to do with one individual cell, there might be other cells suspended in those layers that are just as relevant and can feed into that algorithm as well, or that comprehensive analysis. That will lead to a better diagnosis. So volumetric scanning gives you true universal focus, multi-layer imaging. It's tolerant of all the tissue types because it's Z-stacking. With Z-stacking, you can look through a suspended tissue type like an aspirate for cells that are floating in the middle of it. You don't have to only look at the surface plane. And of course, there is more data. Whether you choose to use it or discard it is up to you. And with that, you can start feeding intelligent analysis, right? Everyone's heard of AI. It's the catchphrase of the industry for 5, 6, 7 years now. If you use AI algorithms, opportunities are created. It might use or create predictive analysis. I got an example of this below, but the foundation of good AI is data, and lots of it. The more data we feed an intelligent algorithm, the smarter it becomes because it's got a built-in feedback loop. So if you fed an AI algorithm a single image where healthy cells were round and unhealthy cells were square, it would evolve to look for square cells and mark them as bad. If you fed that same algorithm a collection of images where healthy cells are round, just like before, and unhealthy cells vary from square to oblong to triangular, it'll now evolve to look for cells that are not round. Before it looked for cells that were square, but now it's going to look for cells that are not round and mark them as bad. That makes it more powerful. That creates predictive analysis. It now knows to look for things that aren't healthy instead of looking for things that are diseased. And in looking for things that aren't healthy, you don't have to tell it what that is. It's going to find it and learn from it. Now imagine if we can add a third dimension. So a round cell is different than a spherical cell. So if you now say spherical cells are healthy, but while it may look round from an overview, imagine if it was oblong from a side view. Now that third dimension means that that cell that looked healthy might not have been healthy. This is a very oversimplified example, but hopefully it helps you wrap your mind around the idea that more data is good and predictive analysis can be created by extended good data. So combining that with the enhanced data, we will optimize the patient care. What are the possibilities? I kind of made a few formulas. Multi-layer images plus enhanced data equals exponentially more powerful analysis. We are supercharging our image analysis by giving it all that extra data from the images and the ancillary data. Conditional processes equals more impactful diagnosis. What does that mean? Conditional processes means if we get a breast tissue with a certain biomarker from a woman in her 40s, mid 40s, whose family has a history of breast cancer, without you even tasking the system to look for that cancer, it could look itself because it's taking that data and it's using it to drive the process that it performs. And of course, most important for AI, output equals input. Remember, I said there's a feedback layer to that software, which means as it learns, whatever it puts out, it's going to learn from because it loops it back in as input and learns continuously. So adding three-dimensional data into an algorithm, now we can more greatly find and identify the things we are looking for. We can drive the processes that will be created by that data, and then further refine the output data, which will, as I point out in that last formula, enhance what we do next, and so on, and so on, and so on. Imagine right now, if we stay with monolayer, if we stay with limited data, if we confine ourselves to that realm, we will handcuff the industry to stay with what it's always done, instead of growing and evolving to what it needs to be. So conclusions, well, we are well on our way to what is possible, and we don't even know what that means. I don't know what that means. I just know it means more than it means today. It does revolve around data. Without good data, nothing can evolve the way it needs to. And most of all, it requires a new viewpoint. The metric we should all be focused on is data, more of it and better. It takes a little longer to capture more and better data, and we should take the time to do it. Images are part of that data, and it's time to evolve into the next generation of image capture as well. We can't keep looking at single monolayer capture. It will work, but it will be limited. And finally, we need to integrate all of these steps together so that each step may enhance the others to create the best overall process. Analysis will change from being reactive, as it is now, to proactive, using that data to automatically drive its use. That analysis can be done during image acquisition, in partner with image acquisition. It can even drive further image acquisition. The analysis could recognize on a single plane, hey, I see something, I want you to capture 5 more planes. And then you're now adding more data where it's critically necessary. And digital pathology will not only be the capture of an image for an eyeball like it has been in the past, but also the collection of all relevant data, the analysis of that data, and the presentation of not only that image, but also the accompanying data and analysis output, so the best outcomes are realized for all people.
Kevin, thank you. A lot to chew on, a lot to think about. I learned some things today for sure, especially this overall approach around not just the image, but all the data, including the image data. We do have a few questions, and we've got 6 minutes. Kevin, Joanne asked, do all scanners have this volumetric scanning?
No, there's very few that actually do. I can think of one. Pramana embraced volumetric scanning from the outset. We decided we did not want to do what everyone else had already done, and we wanted to set ourselves aside and focus instead of on speed. We wanted to focus on data and quality. And we did. Everyone focuses on quality. I don't want to minimize that, but we focused particularly on universal quality, especially the ability to scan all tissue types. And that's what volumetric scanning can do. I have a feeling more will come along soon enough. I really do, because I don't see a better solution for the future of our industry. If you want to get outside of one ology, pathology, and you want to get into all the other ologies, as TechSite knows, with microbiology, cytology, hematopathology, you get into veterinary care, you can't stay focused on what worked 10 years ago. You have to stay focused on what's going to work 10 years from now.
Thank you. Kyle asked, what are some good guidelines when determining what scanner would be the most beneficial? So maybe I'll respond to that one first, because of course, Kevin represents Pramana today. TechSite, our platform, is compatible with images from lots of different scanners. Typically, the conversation is around what are you looking to digitize? What ology in Kevin's vernacular? And so we start there, and then what are your volume capacity needs? So what kind of image do you need to secure from a specific sample type? And then what are your daily volume throughput requirements? Those have typically been some inputs. You're hearing on this webinar, of course, technology that should also be considered around, are you getting enough data? Are you getting enough dimensions to make clinical decisions? Pramana also has a lot of experience in the archival space, not just clinical. So that could also give some different inputs on how to determine what scanner might be most beneficial. Kevin, if you took off your Pramana hat and thought about all your industry experience with other manufacturers as well, what would you add about guidelines?
So the first thing is always look at what you need. Ask yourself the same question that I ask the first time I meet a customer, which is, what are you doing with digital pathology today, and what do you want to do with digital pathology tomorrow? And once you figure that out, that answer, and only your institution can come up with that. Some people say we just want to do frozen sections. Other people say, you know what? We have an institution-wide initiative to embrace digital pathology every way we can. What's the best way to do that? That's going to dictate the platform that best serves your needs. You might only need a small low throughput scanner just for consults, just for tumor boards, just for frozen sections. You might need one just for research. You might need a very large platform for doing high throughput scanning on a very large basis. It changes for every customer. And look at all the ones out there and pick the best one that suits your needs.
Wonderful. Cass asked, I saw examples of transmitted light scanning. Is there a fluorescent light application as well?
So I love that question. I used to work a lot with fluorescence. So volumetric scanning and fluorescence works very, very well. Fluorescence already looks three-dimensional when you look at it. If it's set up right with good exposure times and not a lot of background, it's stunning to look at. And when you get to the third dimension, you add a lot into it. Now, the problem is fluorescence takes a lot of time. It's a very manual setup. So up till now, there are no high throughput or accelerated time fluorescent scanners with Z-scan capability. There are plenty with Z-stat capability. They're just a very manual process, and it takes time. But yes, it's very important to it, and volumetric imaging will apply greatly to it. But right now, I don't know of anyone out there that's truly embracing accelerated volumetric imaging in the fluorescence space.
And I think we've got time for one more, Kevin. Rick asked, and I think we have a couple that we won't get to. TechSite will follow up with you individually. Rick asked, does scanner digitization remove the need for microscope confirmation of positives or diagnostically significant objects?
So that's a question that only the institution can answer. FDA approval grants the use for digital pathology to be used for primary diagnosis. And if you buy an FDA approved solution, you can do that. You're still going to validate it in your institution to make sure it meets the needs and the processes you want it to do. If it is not an FDA approved solution, there's always other ways that right now, no one actually knows how it's going to shake out. I don't even want to speak to it because I am not an FDA regulatory expert. But we all know that in the past, you could validate and use a system that you validated in your own institution that was not FDA approved. I don't know what's going to happen in the future, so I'm going to leave that one completely alone.
Kevin, we really appreciate your expertise and insights today. You've been a long timer in digital pathology, and sincerely appreciate you as well as our partner Pramana, as we've learned a lot more today about scanning as a whole. Again, reach out with any questions, and thank you all for tuning in to this latest episode of Pioneers in Digital Pathology. Have a wonderful day.
Thanks, everyone.